Welcome students. Today we will study digital image processing. This is a final year, that means fourth year 7th semester paper. This is an elective paper having the code EC703A. I am Kaushik Pal, Assistant Professor of Department of Electronics and Communication Engineering, Guru Nanak Institute of Technology. Our today's topic is fundamentals of image restoration. In the previous class we have studied some of the fundamentals of image restoration. Now the remaining portions will be done today. So in the last class what we have studied what is image restoration, why image restoration required, what are the applications area or image restorations, different noise models and different techniques of image restoration techniques. We have discussed all these using some examples. Some input images has been given and also the output images has been gathered from there. Now we will just recapitulate a little bit of them and we will move forward with new topics. Now this is the key stage in digital image processing, which is known as image restoration. Here we can see this is the third steps, where the first step is for the problem domain. The image is being accused because this image acquisition is the process by which we can acquire some image, and on that particular image we will do the operations. So this image acquisition technique is very much important to have the raw image on which the processing will be done. After that, if small corrections needed or different type of image enhancement quality, if the quality of the image is being enhanced, so that can be done through image enhancement technique. The aim of image enhancement technique is to upgrade the quality of the image. Then the image restoration comes. We have also discussed in the previous class that what is the basic difference between the image enhancement process and image restoration process. Image restorations is not used to upgrade or enhance the quality of the image, but to have that particular image which was distorted or destroyed. So image restoration means the image is being restored or the image is being retrieved from the degraded one. So image restoration is not same as the image enhancement process. Here one example has been given where we can see noise has been removed. So the input image has much more noise, whereas after this noise removal technique, so we can have the output image which is much more clear in compared to the input image. So this is one type of image restoration technique. So lots of filtering techniques are there which are generally being used as image restoration process. So here we can see some of the portions were missing in the image that can easily be retrieved from the original image to the output image. So we can say that image restoration is a very important key stage in digital image processing technique. Now moving forward to the next slide. This is image imprinting. So this is the image imprinting is also known as restored image. So why this type of restorations is required, or what is these restorations or imprinting? So this is nothing but reconstruct and corrupted or destroyed parts of a particular image. Here we can see the input is a damaged image whose some portions are totally damaged, and after this restoration algorithm used, we have obtained the restore image which is much more clear from the input image. So some portions which were degraded or destroyed, that is easily be retrieved in the restored image. So image restoration is the very important portions by which we can have very poor quality or very ancient image, and we can reconstruct them. So it has a wide applications area in nowadays. Now if we go for the definitions, what is image in painting or image restoration? Image restoration attempts to restore images that have been degraded. First of all, identify the degradation process and attempt to just the opposite or reverse of it. Almost similar to image enhancement technique this is, but it is not same as the image enhancement technique. This is but more objective, not subjective. So here we are having two images. The input images is the degraded images, and the output images is the restored images from the degraded images. So here we can see the second image or the output image is much more clear than the input one. Now we will discuss in this class some of the noise models. So here 7 noise models are there, 7 types of noise we will discuss, different type of noise and their probable source of those particular noise, which will also be discussed here. The source of the noise is also very much important, as the type of the noise totally depend on the source of the noise. So the first one is Gaussian noise, which can be generated by electronic circuit sensor noise. Then the Rayleigh noise, which can be generated by range imaging. The next one is Erlang or gamma noise, which can be also generated by laser imaging. And the next one is exponential noise, which can also be generated from laser imaging. The next one is uniform noise, and after that we can see the impulse noise. The impulse noise is also known as salt and pepper noise, which is generated for different type of faulty switching. And the last one is the periodic noise. So these are the different type of noise, or we can consider them to form different type of noise models, which is very important in case of image enhancement technique. Moving forward to the slide, we can have the explanations of them. We can see some of the expressions and the plot of them. So we will start with Gaussian noise. Here the term probability density function is very much important for all the case of each and every noise. So we should calculate the probability density function, and we should also see the corresponding plot of the several noise. The first one is the Gaussian noise. Here the probability density function of Gaussian random variable z is given by pz 1 by root over of 2 pi sigma e to the power minus z minus mu square by 2 sigma square, and the equations and as well as the corresponding plot has been given at the right side. The next one is Rayleigh noise. Here also the corresponding probability density function, the mean and the variance and the plot has been given. So if we want to discuss the probability density function or PDF of Rayleigh noise, that is given by Pz is equals to 2 by b z minus a multiplied by e to the power minus z minus a square by b. This is for z greater than is equals to a, and if z is smaller than a, then the value should be equals to 0. if we calculate the mean, it should be mu is equals to a plus root over of pi b by 4 and sigma square, that means the variance is b multiplied by 4 minus pi divided by 4. So this is very much useful for approximating skewed histograms, and the plot has been also given here. So we have to carefully see the corresponding equations for probability density function, the mean and the variance, and also the image of the plotting. The next one is either known as Erlang noise, which is also known as gamma noise. Here also the probability density function, mean, variance, and the plot has been given. So if we go for the equations, the probability density function for Erlang noise is given by Pz. The value should be equals to a to the power b z to the power b minus 1 divided by b minus 1 e to the power minus az for the value of z greater than equals to 0, and the value should be equals to 0 for z less than 0. The mean value is given by mu is equals to b by a, and the variance is sigma square is equals to b by a square, and the corresponding plot has been given. So here we can see we have to use the factorial values. Now this is an example of Erlang gamma noise. Now if we move forward, the next example is the exponential noise, whose plotting and probability density function has also been given. The probability density function for exponential noise is given by Pz is equals to a to the power minus az for z greater than is equals to 0, and the value will be 0 for z less than 0, whereas always a greater than 0. The mean value should be mu is equals to 1 by a, and the value of the variance should be sigma square is equals to 1 by a square. The corresponding plot for exponential noise is also given in the diagram in the right side. So hope you have seen. So we should move forward to the next slide for the next topic. Our next topic is uniform noise. That means from the term it's very clear the noise is being uniform, no abrupt change is there. So the plotting has been given here. So from the plotting we can see the noise is very much uniform. Now if we see the probability density function of uniform noise, which is given by Pz equals to 1 by b minus a, if the value of z lies between a and b, that means z should be greater than is equals to a and less than equals to b, and the value of Pz should be equals to 0 in all other cases. So if we go for mean and variance, the value of mean mu equals to a plus b divided by 2, and the value of variance is sigma square is equals to b minus a whole square divided by 12. Now this is impulse, salt and pepper noise. So salt and pepper noise is also known as impulse noise. We already know that this type of salt and pepper noise is generally generated for low light imaging technique. That means if the light is less, this type of salt and pepper noise can be generated. The probability density function of bipolar impulse noise is given by Pz is equals to Pa for z is equals to a, Pb for z is equals to b, and in all other cases the value should be is equals to 0. Now some examples has been given here. So this is nothing but the periodic noise. So this periodic noise arises typically from electrical or electromechanical interference during the image acquisition. That means when the image is being captured or when the image is being acquired, then if there is some issues which is related to either electrical or electromagnetical interference, so this type of periodic noise may occur. Now the only type of this specialty dependent noise considered in this chapter. So this is a special type of noise which is also known as the only type of specially dependent noise considered in this chapter. So this is generally happens if there is some electrical or electromagnetical interference. Now there are some illustrations, we have to make them clear. We have to see these images very carefully. There are there are total 6 number of images. So the first images is the images with the Gaussian noise, the middle one is the image with relay noise, and the last one is images with gamma noise. So all the 3 images has different type of noise, and in the next row the corresponding images histogram is depicted. So the first one is the histogram of the image having the Gaussian noise, the second one is the histogram of the image having relay noise, and the third one is nothing but the corresponding histogram representation of the image having gamma noise. So some of the images with some noise and their corresponding histogram has been given here. This is the first illustrations. Now if we move forward to the next illustrations, we will have this type of examples. Here we are having the second examples. Here also some images are there with some noise and their corresponding histogram is also given. So here we can see the first images having the exponential corresponding noise, and its histogram is also given in the second row first image. Now for the uniform noise, it is almost like a square pulses in case of histogram diagram, and for the salt and pepper noise we are having just 2 spike. So that means this is the histogram of the salt and pepper noise attack image. So hope it is clear. So we should move forward to the next slide. Now this is the estimations of noise parameters. So noise parameters are very much important because depending on these parameters the noise characteristics and the amount of noise can easily be understandable. So these estimations of noise parameters is very much important. We have to keep in mind some of the points. The periodic noise is generally estimated by Fourier spectrum, and all others are corresponding generally estimated. Try to compute the mean and variance of a sub-image S containing only constant gray levels. So here 3 images has been given. We can have all the corresponding images. Here histogram computed using small strips shown as these in the image. The first one is the thresholding, the first one is the corresponding histogram of a Gaussian noise image, the middle one is relay noise image, and the last one is the corresponding histograms for the uniform noisy images. So these 3 are the examples of these different histogram of having 3 different noisy image. This is the restoration in the presence of noise in spatial filtering. So some of the spatial filtering we will discuss here, so they can be used for restoration purpose, and if there is only noise is there. So the important thing is the mean filters. So the different types of mean filters are there. The first one is arithmetic mean filters, which is very much important, then the geometric mean filter, then the harmonic mean filter, and the last one is contra harmonic mean filter. So the contra harmonic mean filter and the harmonic mean filter equations has been given, which you have to be follow very carefully. And here Q is the order of the filter. Q must be greater than 0 for eliminations of Pieper noise, and Q must be less than 0 to eliminate the salt noise. So if you want to remove the Pieper noise, then the value of Q must be greater than 0, and if we want to eliminate the salt noise, the value of the Q must be less than 0. So these are the key factors for these median filters to restore the corresponding image in presence of noise, that is also known as spatial filtering. Now some illustrations is also given here. We have to see all the images very carefully, and from there we have to understand what is the input image and what is the output image. Here the first one is the X-ray of any corresponding circuit board, and the corresponding second image is the image corrupted by additive Gaussian noise. The third image is result of filtering with an arithmetic mean filter of the size of the mask is 3 cross 3, and the last image, that means the fourth image, is the result of filtering with a geometric mean filter of the same size, that means the size should be 3 cross 3. So here we can see the first image is a very clear X-ray image of the any type of circuit board, and if deep Gaussian noise is there, so after this addition of the Gaussian noise, the second images will be there, and if we want to get rid of that particular Gaussian noise or to remove the Gaussian noise to restore the image, we should use the third, we should see the third and fourth images. The third images is the result of filtering with an arithmetic mean filter of the mask size 3 cross 3, and the fourth image is the result of the filtering with the geometric mean filter size is 3 cross 3 mask. Now if we move forward to the next slide, this is another illustrations or examples, so it can be considered as examples too. Here also some corrupted images has been taken and some of the filtering technique has been applied, and we can see the quality of the fourth images is quite better. The quality of the third and fourth image is quite better than the first and second one. Here the first image is corrupted by Pieper noise with a probability of 0.01, and the corresponding second image is the image corrupted by salt noise with the same probability. So first one is corrupted by corresponding Pieper noise, and the second one is corrupted by the salt noise. Now we will use the filtering technique. So where in the third images the result of filtering with a 3 cross 3 contra-harmonic filtering to order, the order is here 1.5 and the plus 1.5, and the corresponding last images is the same contra-harmonic filter we have used, but here the value of Q is minus 1.5. So we can see the quality factor Q is once 1.5, and in the last one it is minus 1.5. So we can see the corresponding output of this noisy image. One is image having salt noise, and another image is having Pieper noise. So both of them are very much clear using this type of contra harmonic filter. So output image is restored from the distorted input images. This is another illustrations or examples 3. So here the results of the selecting the wrong sign in this contra harmonic filtering has been shown. Here in the first image the result of filtering with a contra harmonic filter of size 3 cross 3 and Q factor is 1-1.5 has been given, and the second one is result of that particular filtering using the Q factor is equals to -1.5. So here the filter has been selected wrongly, so that the quality of the image is not at all upgraded but it degraded. So hope students it is clear to you that choice of this type of filter with the proper Q value is very much important. Now this is another order statistics filters. So we have to keep in mind some of the points, though they are very much important, which is the median filters, then max and min filters, then midpoint filters. It is noted by f cap xy is equals to half of maximum of GST plus minimum of GST, where the value of ST is given by as SXY, and the fourth point is alpha trimmed median filter, which delete the d by 2 lowest and d by 2 highest gray level values of GST in the neighborhood of XY. The average value is given by f cap xy is equals to 1 by m multiplied by n minus d summation of ST subset of is equals to SXY GRST. Now this is another illustrations from where we can see the first image is corrupted by salt and pepper noise with probabilities PA equals to PB is equals to 0.01. The second image is the result of one pass with a median filter of the mask size is 3 cross 3. The third one is result of the processing of the B with this same filter, and the last image is result of processing C with the same filter. That means initially the image A has been given as the input image, and after using the median filter of the size 3 cross 3 we are getting the image B. Now if we use the image B as the input and use the same corresponding median filter, we can have the output as C. And if we again use the C as the input in that particular filter again, that means the median filter having the size of 3 cross 3, we will have the output as D. So after this 3 iteration process, we can see the quality of the image is much more better. That means whatever the informations were destroyed in case of image A, all are there in case of image B, image D. So students, hope from the image it is clear to you that how the salt and pepper noise can be easily reduced using this type of median filter. So moving to the next slide, we can have another examples or another illustrations which is here. So the first image is the result of filtering with a max filter of the size of 3 cross 3, and the corresponding second images is the result of that particular filter with a min filter of the same size. That means the size should be 3 cross 3. Here the size is 3 cross 3. So the first one is the output of a max filter of the size 3 cross 3, and the second one is the output of a min filter of size 3 cross 3. So this is another examples of filtering techniques. Now if it is clear to you we will move forward to the next slide. So this is another illustrations or examples 3, where we can see six sets of images are there, and some of the images have very good quality and some of the images are bad quality. That means some of the noise are there, and using some filtering technique we can get rid of those noises. So the first image is the image corrupted by additive uniform noise, and the image B or the second image is image additionally corrupted by additive salt and pepper noise, which is given in B. Now this is filtered with a 5x5 corresponding filter, and in C, arithmetic mean filter we have used. For the D image, that means the fourth image, the geometric mean filter has been used. For the fifth image, the median filter has been used, and for the last one, the alpha tripped mean filter with D is equals to 5 has been used. So you can see the quality of the last two images is much more better than the previous one, and the last image is mostly similar to the input image. So all the images can be described and they can be seen very clearly. So students, whatever we have studied in this class, that has been summarized here. So if we recapitulate that, what points we have discussed in this class, the first is what is image in painting or image restoration. That means what do you mean by image in painting or image restorations, how it is very important in several image processing steps. Now we have also studied several noise models with some examples or illustrations. Among them we have covered Gaussian noise, which has been developed through electronic circuit sensor noise. Then we have studied relay noise, which has been generated through range imaging. Then Erlang, which is also known as gamma noise, and that also be generated by laser imaging. Then we have gone through exponential noise, which has been generated from again laser imaging. Then the uniform noise, and then the very popular salt and pepper noise, which is also known as impulse noise, and that has been generated through faulty switching. And last, the periodic noise. So all these different noise models has been discussed with some examples. Then we have gone through the estimation of different noise parameters, how we have calculated them, that has been shown there. Then we have studied restoration in the presence of noise only in spatial filtering with 3 examples or illustrations. And at the end we have studied the order statistic filters with 3 illustrations or examples. So these were all the topics which we have covered in the class. So hope students, whatever we have gone through, that is clear to you. So if you have any queries, you can ask me. My mobile number and email address has been given. You can consult 2 books. One is R. Gonzalez and Wood's books is there, Fundamentals of Digital Image Processing, and another book is there, that is also image processing, which is written by Anna Durai and N. Sanmugalaxmi, which is published by PHI Publications. So you can use these 2 books for your reference purpose. Thank you again.